shit's about to get real. So this is now, we're going to do analysis of variance until the end of March. Okay, almost the end of March. That's what the course. Run!
Hi guys.
Fly, Fleons, fly. Beth reference? Nobody? What do they teach you guys in school? Yeah, we're talking about analysis of variance all the way through the rest of the course, pretty much, except for a little bit of time we'll spend on multiple regression. Now, the thing is, this stuff, I think most of you probably learned a little bit of ANOVA in 21-26, is that correct? Mm-hmm. Right? Okay. We'll be doing it this part, so this is sort of review-ish. We'll be doing this, though, at a bit of a higher level, more of a conceptual, theoretical level, than you would have done it in 21-26. Okay. We have t-tests, z-tests to deal with differences between two groups, or between one group and a mean. That's the thing we do. And you know about those, and you've dealt with those. Sure. What if we have more than two groups? Okay, so which is often the case. You know, almost any experiment you read has more than two groups. Okay, it's not like it's an uncommon thing to have more than two groups. So let's pretend we have three groups, and they're different levels of A. Group A1, Group A2, Group A3. This is a notation you'll see me use quite a bit. It's the factor A. It has three levels, 1, 2, and 3. Here are the scores. I don't know what this is measuring. I don't care. The numbers don't know where they came from. But the mean for group A1, for level, so group 1 in factor A is 84. A2 is 74, and A3 is 59. Okay. Those numbers themselves aren't exceedingly important, except that whenever I have ever taught this and didn't put actual numbers up, someone said, could you put some real numbers? So I do. We're not going to calculate anything with these, but it does show you. One could. And in fact, we could do it by hand. It's not that hard. But why? But, so I can refer to what, let me just go 84, 74, and 59 means. Okay. So I can refer back to this easily, 85 and 90, 77, 67, 80, 75. And what do we got for the final group? 52, 60, 52, 60, 69. Okay, so now I can refer back to this if I feel like it. So we've got three groups. This is a very common and clearly a very simple kind of experimental design. It's not something that would faze you in any way. So the question you should ask yourself is, why do the scores vary? What are they the same? Why are all these, so these are the means here at the bottom, but why are the other ones here, the matrix, the 3x3 matrix there, what if they all have the same scores? Right? Nobody else coming? Because the door locks. It's really funny. Well, I guess you're asking then, what are called the sources of variation? That's what we're asking. Why do the scores vary? It's because, so what are the sources of that variation? Can we break it down some? Or break it down yo, as the kids say. Word. So, well, there's individual differences. We all know that. These are supposed to be, I'm thinking these all as being different people. Let's pretend these are scores on some kind of test. I don't know. Well, there's individual differences. Right? So, let's see. We have any natural groups of, we did look. There's a group of 3 here. Here. There's a group of 3 here. And then we've got a group of 5. That's not so good. So then move 3, group of 3. Okay, so we have 3 groups of 3. There you go. Or 4 groups of 3. That's good. I just didn't want to include you guys. 3, 3, 3. To hell with you people. So, okay. You're all different people. Right? You're all different. So that's one reason you're going to get different scores, correct? That follows, right? Everybody's different. Everybody is a special, different person. And, that was a little sarcastic, by the way, but everybody is different. You have different abilities, different backgrounds, different ages, different, let's see, guys there, yeah, different sexes, different ages, or gender identities if you want to go there. Do it that way. What else we got? Different courses you've taken in the past. We can go on and on. Okay, individual differences. That's the reason your scores are going to differ. Sure. Sure. And let's pretend our experiment is, let's make it exceedingly mundane. It's sitting in the first 2 rows, or these last 3 rows, or these. Okay, it's an exceedingly mundane experiment. This is what affects your, this is going to be one group, another group. That's what A is. Row, place, position, thingy in class. Quadrant. Bottom right, top left. And ignored people. Okay. Also, the group differences, it could be, I'm pretty sure that there would be no effect of sitting in a certain quadrant in the classroom, but, or it's exceedingly tiny, but let's pretend we have a reason to guess that there would be something like that. The fact that you belong to a group, that you have been treated differently by me, I'm the experimenter. That's discrimination. It's science. I thought that was kind of funny. Apparently no one else did. I don't care. You people obviously don't know good humor when you hear it. Okay. Does that make sense? Individual differences and group membership. That's the 2 really key things. Yes? Make sense? Okay. So any score, now we can make a model of a score. Any score, any of these naughty scores, is a sum of a few different things. There's a base level of you being just a member of the human race, of our species, of being H. sapiens sapiens, of being anatomically modern humans. That's what H. sapiens sapiens are. Then there's group differences. By the way, they can raise your score or lower your score, group differences. Everybody starts out the same, being a human. Is that a show, Being Human? Yeah. It's not what I'm talking about. Not a bad show. There's an English one and an American one. The English one's a little bit better, but not a lot better. People are always like that, eh? Oh, English TV's so much better. There's good stuff everywhere. I only watch shows that are reported. There you go. You're excellent. I watch a lot of shows like that, but I also just binge watch. I'm always watching The West Wing. Always. I'm in my 11th watch through of a 7 season, 22, 23 episode series. I just keep watching it. Yep. I live on the edge. Base rate of just being existing. Then you can be in a group that's going to raise or lower your score, and then your individual differences are going to raise and lower your score. So you're A1, you're A2, you guys are A3. Okay? So there's an effect of being, something happens to be an A1, something happens to be an A2, something happens to be an A3. Then there's individual differences. That's the level of individual you are. Whatever we call it level, that sounds like it's rank. It's not. So being Enya and being Sam and being Emily and being Serena, they do things to your scores. That's your individual differences. Does that make sense? Well, they can raise or lower your scores. You can sit here in your mind and pretend it raises or lowers your score. Do what you wish. Okay. So does that follow? Makes sense, right? Like that's just intuitively. When I said math, that doesn't look very mathy. Any score equals the sum of 3 things. It's easy, right? But does it make sense that we've exhausted everything? It's probably a little simplistic, but we've exhausted everything. Or we could write it out in Greek letters, which is more fun. Makes us sound smarter. X equals mu plus tau plus epsilon. Mu is the grand mean. That's the immediate unit thing. Tau is for treatment. And epsilon is for error. It's funny, in this case, error actually doesn't mean mistake. It means stuff that we can't account for due to group membership. Okay? Gotta remember that. X equals mu plus tau plus epsilon. Okay? Bloody hell. Okay. That's actually called the structural model of analysis of variance. Structural model of ANOVA. X equals mu plus tau plus epsilon. Any score equals the grand mean plus the treatment effect plus the error. Some books will use Y. In fact, all the way through graduate school I use Y. Our book uses X, so I switched to using X. It doesn't matter. It could just be Steve equals, you can call it oranges. It doesn't matter what it's called. You go with X. And don't be afraid of the Greek letters. They're just used to represent things. It's just short form of any score equals the grand mean plus the treatment effect plus individual differences or error. Okay? It's just a way of writing stuff out. It's nothing to be frightened of. Okay. Questions so far? You guys okay with this so far? Did you in 2126 learn this? Probably not. Yeah. Okay. So this is where we've now departed from 2126. Bye, 2126. See you later. Have fun over there, Nadine. Dave's driving from here on in. Which is a mistake because I'm going to crash this thing. I can't see a freaking thing. So, those of you who I taught brain and behavior last year know about the incidents daily where I would just move chairs out of my way because I kept walking into them. When they first put, I think I told the guys in brain behavior last year, when they first put that clear podium in NW200, I ran into it because I couldn't see it. And then I went on about a 5-minute profanity-laden rant about, making fun of the blind guy with a clear piece of furniture. It's on the internet. I forget what class it was in. I think it's brain behavior 2012. So you'll look that up. You have to find the class it was in. Okay, back to this. Does this make sense? You're okay with this, right? Okay, because everything now will grow out of this. If you get this, this is the basis for everything we do until the end of March. Until just past the Ides of March, which you should beware. At least someone got that one. I'm trying to do a lot of Shakespeare references today. Glams thou art and Cawdor and shalt be what thou art promised. Yes, I'm doing a Lady Macbeth thing. Because I had to memorize something in school. Let's make an assumption. Oh, that looks a little mathy. It actually isn't that bad. We're saying mu1 equals mu2 equals mu3. Mu2, of course, my favorite band. So mu1 equals mu2 equals mu3 equals ... equals mu k. There are k groups, so we're going to say all the way up to k, all the group means are equal. That's all that says. It's HO. And HO also says, so therefore the variances are equal. Sigma squared sub 1 equals sigma squared sub 2 equals sigma squared sub 3 equals ... equals sigma squared sub k. It's HO. It just says they all actually are from the same population. Same population means same variances, right? That makes sense, doesn't it? Okay. So HO is true. That's an assumption we're going to make. Every statistical test that we'll talk about in this course makes that assumption, that HO is true. T-tests make that assumption. Z-tests make that assumption. The simplest possible test you can think of, a sign test, makes that assumption. Okay, so far? Does that make sense? That's a sensible assumption, isn't it? We're going to try to show it's not true, but we're going to assume it is. Because we always start out by assuming HO is true. Then we try to reject that assumption. Okay, so that's all. I'm just putting HO into mathematical terms. That's all that is. It's not something to be frightened of. Unless you scare really easily for some reason. Greek letters, ah! And you have to, the word for Greek letter phobia would actually be in Greek, which is fascinating when you think about it. I really have to try to make this stuff interesting even to myself. This is called the null hypothesis assumption. That's all this is, okay? All right. More assumptions. The scores are randomly and normally distributed around the grand mean. That's okay. We can violate the crap out of that. Randomly, sure. With one score, the value of one score doesn't tell you what the value of another score is. It's a random process. And it's normal. We can make up, that's a reasonable assumption. This one we can't violate, that the observations are independent. I've talked about that before with t-tests, right? So if I know Emily's score, I don't know Sam's score. I can't know anything about it. Because in the model, which just says any score equals mu plus tau plus epsilon, it doesn't say unless you're sitting beside Emily. It doesn't mention it anywhere. Right? You could build that in, but then we'd be doing an entirely different procedure. That's not there. So the observations are independent. So it's normal and independent. And all sources of variation are accounted for in the model. So there isn't anything extra that we haven't accounted for in x equals mu plus tau plus epsilon. Okay? Those are not ridiculous assumptions. We're not going out on any limbs here. But for the math to work, these things must be true. For the math to work, that is way behind this. I'm going to show you some of how the stuff's derived today, but there's stuff way deeper than this. There's a lot of assumptions that are made. These assumptions are made, and they allow you to do mathematical proofs. And you guys probably remember, and it may be a long time ago in a galaxy far, far away, that you have done proofs in math. You were in high school, it was a long time ago, but you've done it. And oftentimes, doing a proof or proving an identity, something like that, you would start by saying assume, or even doing what's it called, Euclidean geometry. Prove that this angle equals this angle. You would always start out by saying assume. So that's all this is. Those assumptions are there because they allow the math to work. The deep math that you don't have to know. That if you're lucky, when you go to graduate school, you won't even learn it there. If you're lucky, you'll have a prof that says it doesn't matter. That doesn't matter. You don't have to know that. Once you understand it intuitively, that's what they really say. You have to be intuitive about it. I think I told you guys, though, he also said all undergraduates are stupid. So, they're all stupid, Dad. They're idiots. He was kidding-ish. He was the greatest. Damn, he was a good teacher. And I watched him teach undergraduates, and he did not think they were stupid. He would just say that to me. And the rest of our graduate student class. I think to build us up. You're so smart, that kind of thing. But it was always about, and I agree with him, it's always about understanding this stuff intuitively first, and then look at it and go, oh, now I see why that math makes sense. So the stuff I'm going to show you today is going to look kind of a little bit mathy, a little proofy, and it isn't. It's more there to help you understand where it comes from. That's why I am doing this. Okay. Let's look at variance, shall we? That sounds like fun. Said no one ever. Even R.A. Fisher was like, I'm so bored inventing analysis of variance. Okay, sigma squared sub 1 or sigma squared sub 2, these are the group variances in the population, are roughly equal to, that's what the waving equals means, S squared sub 1, S squared sub 2. We know that because S squared is an unbiased estimator of sigma squared. That's all that's saying. So I'm just extrapolating from this thing that we know. I'm going to say that sigma squared sub epsilon, in other words, the error variance, is due to, or is roughly equal to, the variance of all these numbers. And we would all accept that. Which is equal to, this is a weird thing to think of, is actually equal to the variance of each group divided by the number of groups. So we'd here have this, we'd have, that's the means. We'd also have variances. So this would be S squared sub 1, S squared sub 2, and S squared sub 3. Okay? If we average those variances, that sounds weird, but if we average those three variances, we get an estimate of the variance. Does that follow? Does that make sense? It does, doesn't it? This is not that bad. That's all this says. It just says it in fewer words and with fewer Scottish accent and things. I was me doing impressions of my graduate school stats book. That's not in there anywhere. Are you good? You get this? I really need you to ask questions if you have. But you're really okay?
No.
Okay, what do you want to know?
I still don't understand the J.
Oh, J just means it's an index.
Okay.
Okay, for groups.
Okay.
It means all groups?
No, it means
Any given
J was group 1. J, when you do summation, this should say J equals 1 up to K. So if you write that, write this. So what? First one, you make J equal 1. You go S squared sub 1 plus S squared, you make it equal 2 plus, and you keep going, you get to K. That's what the J's are. I'm sorry. I forget that it's been a while probably since you did that kind of stuff. So the J's go from 1 up to K. Group J equals 1 is group 1. J equals 2 is group 2. J equals 3 is group 3. Then we stop because we have K groups. K is 3 in this case. Yep. Does that answer your question?
Yeah.
Yeah? Okay, good. Good. Thanks for asking me, by the way, because I totally forgot that I didn't put the indices there. What's wrong? You look concerned.
Why does that all equally track?
Well,
I just don't understand.
okay, that's okay.
Why sigma
Why
equals S?
Well,
J.
this is just all the variance. Sigma squared, like all the variance of all the 9 people here, or the 90 scores.
Mm-hmm.
If we're assuming, what's the null hypothesis assumption again? It says that all the groups are equal. Then any variance in scores isn't due to groups. It's due to individual differences, right? So the variance of all these scores, is simply due to error. Okay? And then that's also the variance of all the scores. It's just a statistic, not a parameter. And then we can average the group variances to get this. So they all equal the same thing. That's a good question. Other questions? So we're partway there. Almost went with the Bon Jovi thing and decided against it. When you're young and stupid, you get really worked up, especially if you're a guy, as a rule I find this, about music. And you're very sort of ideologically pure about music you listen to because you're an idiot. I once left a party with some Bon Jovi on. That was like my friend Dee, and I said, take that shit off or I leave. She said, well, I like it. I said, well, that's it, I'm going. Because I'm an idiot. I totally had a crush on her. It was horrible. Such an idiot. I don't think it helped, but that didn't help. Let's just say that. I know women, they really dig when you criticize their music and leave because they put a song on, right? Oh, look, hypercritical, nervous guy. Ooh, hot. No, I don't think the world works that way. I don't think the world works that way. Didn't have a lot of success with women.
You're married, so it's okay.
I married my first girlfriend.
Aw.
Well, it's kind of nice, yeah. I married someone who would put up with me.
You might want to edit that out.
No, she knows that. She's well aware of the fact that not many women would put up with me. Or men. Okay. Does this make sense?
Now, yes.
It does? Okay. Still can't figure out how I found a woman that would like me. But that makes sense. Because this is math. This is okay. There's great answers to this. That's a mystery, man. Okay. Okay, this looks a little worse. But it isn't. I'm going to walk you through it. It's what I do. I teach. So, remember the central limit theorem that I told you to memorize because it was important? Hey, here! Look, important. The variance of the means. What's that mean? Oh, that's the sampling distribution of the mean. That's right. That's all that is. Oh, that's true. We take that as a given. That comes from the central limit theorem. The variance of the means equals sigma squared over n, number of subjects. Right? That just is. That's just the way the world works. That's central limit theory. You can't argue with that. That's science. That's real. So that's just a given. Try to find ways to estimate variance. That's all we're doing here. Okay, so the variance of x bar, the variance of these means, that's what that means actually. That's weird, eh? Again, the means don't know where they come from, the numbers don't know where they come from. You could calculate a variance of means. It sounds weird. Be like making a pie out of a cake, but you can. Cake pie. You could totally do that, right? You could put a pie, make a cake, and then put it in some side puff pastry. I might do that when I get home. I don't have any puff pastry. I used it all up to make chicken pot pie on Monday. Okay, leftover chicken was delicious. Okay.
So are these like actual calculations that like we're gonna
You wouldn't do
or,
them.
Okay.
One could, but the calculations you do grow out of these things.
Okay.
But this variance of x bar, that's the variance of the sampling distribution. I mean, that's kind of like, therefore, s squared of x bar, right? That's the variance of these means. I know it's weird. It's making a pie out of a cake, but it's a thing. It's like a turducken. This one's actually easier to get to the end, because the sigma squared that we were interested in is sigma squared sub epsilon. That's the variance of all the scores. Right? Divided by n stays the same. We want to isolate sigma squared sub epsilon. We want to estimate it. So we cross multiply. So s squared sub x times n equals sigma squared sub epsilon. So we take the variance of these means and we divide by multiply times the number of subjects in each group. That's another variance. That's kind of neat. Okay, questions? Does this make sense now? Yeah, it's weird, eh? Like it's kind of strange. We can find two ways to estimate variance pretty easily. Okay. So we have two separate estimates of sigma squared sub epsilon. Two separate estimates. Not one, not three, but two. Both of these things that we sort of derived here, sigma squared sub x bar times n, and sum of s squareds sub j, where j goes from 1 up to k, divided by k, both equal sigma squared sub epsilon. Both those two things we figured out in the last two slides, both equal the same thing, but they're calculated independently, which is neat. And if the null hypothesis is true, remember that is one of the assumptions, this is true. If the null is true, that's actually true. Huh. That's pretty cool. That's called mean squared error on the left. That's called, mean squared treatment. This is called mean squared error. It's sometimes mean squared between groups, mean squared within groups. You'll see that too. I tend to use mean squared error because it becomes a term that we will use throughout the rest of the course. So that's mean squared treatment, mean squared error. Or mean squared between, mean squared within. If you play with SPSS and do an analysis of variance with SPSS, I think it gives between groups and within groups. Means the same thing. And we'll go over a little bit of that on playing with SPSS and doing it, setting up an ANOVA on Tuesday. It's not that hard to do. I really think one of the things you could do as well, go to YouTube and do one-way analysis of variance SPSS. There are 800 guys and 2 women who have made videos, because for some reason it's all these guys that make stupid videos, showing you how to set these things up. So you can even choose them with the best production times. You know. Worst part of YouTube videos, you want to look at something for like 40 seconds, right? It's like, how do you, I don't know. Oh yeah, I got to put up a new range hood. Ours is screwed up, so I got to buy a new one and put it up. I've done that before, but I think, how hard can that be? So I go to Google and find some videos. Install a new range hood. Great. But I got to sit through this guy's 2.5-minute intro where he showed with his like spinning stars and all his bumper things at the beginning, and then it's like, hi, welcome to Do-It-Yourself Install with Mike. I'm Mike, and I'm going to install this now. But first, and then, oh God, I hate YouTube.
Subscribe, comment up below.
That's right. Click up here to subscribe, make sure to comment, or follow me on Twitter and Facebook, also Instagram, and I'm on Google Plus like no one else. Trust me, it's like, don't just get to the thing how to install the thing. See, I intersperse my stupid little comments through this. This is different, and this stuff is boring. Okay. It just bugs me about YouTube videos, right? Or worse is when you're looking for a game walkthrough, and all you want to find is like how to beat that one guy. And some jerk-ass 12-year-old kid. Well, first, don't forget to subscribe to my videos, and also click on my Google ads, and
What's like when you watch makeup tutorials? I bought this pouch here. This lotion.
Here's
I used to remember on this night they went out with this guy, but he was an asshole.
I never watched a makeup one, but that sounds wonderful. What? That's great.
When we talk
Makeup
about products
tutorials
for like an
are
hour
great.
before they show how to use it. Yeah.
First the unboxing. That's another thing too. First the unboxing of the new range hood. No, I don't need to see it open a box. I'm a 51-year-old man with a PhD. I can open a box. I need a box cutter or a knife or some keys. Just show me really what the electrical connections are. If they're going to be hard for me to do, I have to call my friend Jody, who's a contractor. And I look, no, I don't have to. I'll just have to have, Isabel will stand there and it's going to be great. We should video that because it'll be about 7 hours of me swearing. I'm never as bad about when I do stuff like that with my wife as my dad was with my mom. We were putting up a ceiling once, 4x8 sheets of gyprock. I was 12 years old and I had to hold it. And I was this size when I was 12 years old. I wasn't big, I was like 110 pounds, but just tall. And I'm standing there, my brother, who also was standing on a chair doing it, and then my dad built my mom this sort of T-bar thing, and it's 2x4s. My mom's pretty small, it's about 5'2". So she slides this thing under, but she can't get it right. And my dad yells out, "I should have married a man." It's like, what a horrible thing to say. I love my father, and I miss him every day. He died, geez, a long time ago, 9 years ago. But there were times when he was a real jerk. Anyway, we have these two things, mean square and mean squared treatment. They're expected values. They're both, and we figured this out already, they're both sigma squared sub epsilon. That we've already figured, that's what this all came from. The expected value of mean squared error is sigma squared sub epsilon. The expected value of mean squared treatment is sigma squared sub epsilon if HO is true. If HO is true. I'm going to start all the YouTube videos out now with a thing about click here to subscribe and all that stuff. But there'll be nothing to do that. You know. Okay. We're good? So that's if HO is true. What if HO is not true? This is where it gets interesting. If HO is not true, the expected value of mean squared error is sigma squared sub epsilon. The expected value of mean squared treatment is sigma squared sub epsilon plus n times sigma squared sub treatment, something we haven't seen before. Because the null hypothesis assumes that equals 0. It says the null hypothesis says there's no effect. Right? So mean squared treatment is measuring error variance and any other variance that's there. And any other variance that's there is mean squared treatment. Is its treatment variance. We've assumed that. We've said that in our model. Our model says x equals mu plus tau plus epsilon. Under HO, tau equals 0. But what if HO is not true? Well, tau is positive. It must, expected value of mean squared must be less than expected value of mean squared treatment. Why? If HO is true. If HO is not true. Look at those two expressions. Why is that the case?
Because there has to be less of a difference with the treatment.
I don't understand what you mean.
Well,
Just say that again. I think you're on the right track.
Like there has to be less of an effect with the treatment than there is with no treatment. Because
yes, if that was if this was flipped around, you mean?
Oh, then I don't know.
Yeah, okay. No, it's okay. That's okay. No, at least you tried. Thank you.
Oh.
Why must this quantity be bigger than this quantity? Yeah, go ahead.
So then basically it's just kind of the opposite of what you said.
Yeah.
So
it is the opposite of what you said. Yeah, that's why I said I think you're on the right track.
Oh, because I was looking at it if it's true and it was the other way.
Yeah. Remember, with these, the alligator's mouth points towards the bigger piece of food.
Yes, I know.
That's how we were taught that grade too. I seriously remember that one. But anyway, you were saying.
yeah, so the treatment effect has to be bigger than kind of what the control was, or like what the base layer was.
But why would it have to be bigger?
For there to be a difference.
Yeah. But why big? Why? Just you're thinking about it conceptually, which I really like. Both of you are. Like, very good. Mathematically, why is that true? Why must that be true?
Can't equal 0?
Okay, well, no, we're assuming now that mean squared treatment, that there's a treatment effect. HO is false. Mathematically, why must this thing here, sigma squared sub epsilon plus n times sigma squared sub tau, be bigger than sigma squared sub epsilon? What I'm asking is, why can't this be a negative number?
Because it made an effect, so it can't be 0.
Don't think about it conceptually now, because you're right. Conceptually, you're correct, and I'm glad you're thinking of it that way, and that's cool. But also, let's look at this mathematically. Is it possible for this to happen?
No.
Why?
You're not multiplying by a negative.
Yes, because this can never be negative. It's a squared quantity. It must be positive. You both are thinking it so nicely, intuitively, that I almost don't want to do any math. But this should show you something. If that did happen, something weird went on. Because it actually can happen when you calculate it, that this is smaller than this. You go, oh? Yeah, because you violated an assumption. So it can happen, it just shouldn't happen. So if we divide mean squared treatment by mean squared error, which I then wrote incorrectly, mean squared error divided by mean squared treatment, so mean squared treatment divided by mean squared error, flip that around, we should have some estimate of how much extra variance mean squared treatment is measuring. Right? Because the first thing you might think of is, well, when I take mean squared treatment and subtract mean squared error, and you tell how big mean squared treatment was, but what if mean squared error is really a big number? You really want to get a ratio. You want to get a ratio. Don't you? I think you do. How much extra variation mean squared treatment is measuring? Does that make sense? Yeah? It looks like some people are saying yes. I see some nods. I can even sense it. I can't see, but I can sense nods. I can feel it.
Why?
I mean, why?
Why does error over?
It should be treatment over error. That's
Or why does treatment over error estimate that?
mean squared treatment, well, think about it this way. Wasn't mean squared treatment if HO is false? Wait a second, I might have that in my next thing I learned. Well, let me just put that there. It's measuring tau, or sigma squared sub tau, right? Plus epsilon, or sigma squared sub epsilon. So, think of it this way. Mean squared treatment is tau plus epsilon. I know it's n times sigma squared sub tau plus sigma squared sub epsilon. I like just saying it's tau plus epsilon because it allows me to very simply imagine it. So mathematically, that's actually not true, but it's a shorthanded notation that I use. So mean squared treatment is tau plus epsilon. That's MST. And mean squared error is just epsilon. So if we divide that by that, and this must be a positive number or 0. This is now going to give us a ratio of how much extra variance is available that's due simply to treatment. Okay? Does that make sense? Does that help? Good.
Yes.
So in other words, it's giving us tau. And yes, technically it's giving us n times sigma squared sub tau. This is precisely what analysis of variance does. In fact, what I've just shown you is the logic behind and kind of the math behind analysis of variance. This is how it works. This is why figuring out variance actually helps you figure out differences between means. Which I know when I learned this in my second year stats class, just struck me as completely counterintuitive. Why am I calculating variances to find out if means are different? But this is why. This is why. Questions? So, F stands for Fisher, by the way. Is R.A. Fisher developed analysis. Very famous evolutionary biologist. And when there was no way to analyze his data, he invented this. That's smart. So F equals MST divided by MSE. Mean squared treatment divided by mean squared error. Or sometimes called mean squared between groups, mean squared within groups. You'll see that. What's the expected value of F if HO is true? So if HO is true, and here's F up here, tau plus epsilon over epsilon. What's the expected value of F if HO is true?
0.
0. How could it be 0? Because that would mean the top was 0.
1.
You are correct, madam. The tau is 0. You're right there. And let's say that that's what you meant. That's what you meant, right?
Yeah, of course.
Yeah, of course. So, if this is 0, epsilon divided by epsilon is 1. Sigma squared sub epsilon divided by sigma squared sub epsilon is 1. 3 divided by 3 is 1. Oranges divided by oranges are 1. Something divided by itself is 1. A house divided by itself cannot stand. That's Lincoln. It's a bit different. I went with Lincoln that time instead of Shakespeare. Then I was going to reference a song that none of you have heard because you're all too young. It's just funny, and I'm not going to do it. I'm just not going to do it. But
I want to know.
no. How's it go? 2 divided by love can only be sad because 1 is the loneliest number. But 1 is the loneliest number that you've ever heard. That's different song. Those are 2 different songs.
Sorry.
One of them's a bad pop song from 1973-74. And one of them, 1 is the loneliest number, is actually kind of a decent song. Serena looks like she might know one of those songs. I can see from here, again, I can sense it. Okay, that's good. What's the expected value of f if HA is true? Huh. What if HA is true? Greater than 1. I heard someone mumble that. Somebody mumbled it. One of you guys. Right? Yeah, okay. Yeah, it's got to be greater than 1. We don't know the exact number. It's got to be greater than 1. There's a song called The F Word. That's a different thing. I'll probably just dub that into the background of the podcast right now. No, I think I will, actually. Yeah, please.
Okay, so you know how like when we're testing for significance and it has to be like over the 0.05?
Yes.
Does that still apply here in any
It will,
other
yeah.
way?
Yeah, right now we're not even thinking about that.
Okay.
Yeah, but yes, exactly. Yes. It has to be enough different from 1 that we go, there's no way it's 1.
Yeah.
Yeah, that's the decision that ends up getting made. It has to be so different from the expected value for it when HO is true that we say if HO is not true. Yeah. So yeah, you're getting exactly the right thing. That's right. So it's not just if it's bigger than 1, you reject HO. It's if is it bigger enough than 1. Mm-hmm. Yeah. Excellent question. So if HO is true, then mean squared treatment divided by mean squared error will, if HO is true, will be distributed as f with 2 different sets of degrees of freedom. Degrees of freedom for the numerator and degrees of freedom for the denominator. And if not, it will be, if this is not true, if HO is not true, I think is my next point here, it'll be distributed some other way that we don't know, frankly, but what we do when we look it up in a table is we look at that f value, what's called the critical f value, and see what's the point at which we have less than 5% confidence that HO is true, that f is really 1. Is it different enough from 1 that we're confident enough in saying, yeah, it's different? Or what are we, 95 usually, % confident that this isn't true, that HO isn't true? And that's when we then reject. So yeah, you still have to look things up in a table. You still have to look for p is less than 0.05. And you typically, if you did it by hand, you look it up in a table. If you did it with software, it would just tell you. That's a good question. Other questions? So we're going to do something called partitioning the sums of squares and degrees of freedom, which is something we'll do when we talk about every single kind of analysis of variance we do, pretty much. Sum of squares total. Sum of squares is just, do I have that written down? What the sum of squares are? Well, it doesn't matter. The sum of squares are each score, sum of squares total is each score minus the grand mean squared. Each score minus the grand mean squared is the sum of squares total. We're not dividing by anything. That's just called the sum of squares. It's the top, sum of squares is the top part of analysis of variance calculations. It's the sum of squares. Okay? So sum of squares total equals these two things. Sum of squares treatment plus sum of squares error. Those are just the top parts of the calculations, and I'll break that down for you in a second. The degrees of freedom, the total number of degrees of freedom in any design, in this case, in our design, is going to be the number of observations minus 1. Because to calculate the overall variance, we do this. X bar sub g, what I mean. It's just the mean of all of these, in our case here, 9 numbers. We have lost the degree of freedom. So when you partition sums of squares out into their group, so treatment and error parts, degrees of freedom go with them. Degrees of freedom for treatment and degrees of freedom for error. Okay? Okay, now, let's get a little bit more precise. Sum of squares treatment, oh look, that's what I have written right there. Sum of squares treatment, or sorry, sum of squares total is the sum of x minus x bar sub g. X bar sub g is the grand mean. Sum of squares treatment is x bar sub j, that's these. That's those group means, minus the grand mean squared times the number of subjects in each group. So in our case, it's going to be 3 each time. And this here, so look at that, that's a mean minus another mean. This one here is individual scores within each group minus their group mean squared. So we do that all for group 1. So in our case over here, 85 minus 84 squared, 90 minus 84 squared, 77 minus 84 squared, plus 67 minus 74 squared, 80 minus 74 squared, 75 minus 74 squared, plus 52 minus 59 squared, 60 minus 59 squared, 65 minus 59 squared. So we add all those together. That'll give us our sum of squares within groups, you might call that, or sum of squares error. If I felt like it, and I don't, but if maybe you could if you feel like it, but you probably don't. You can expand all this out and prove this. This is an identity you can prove if you were feeling mathy. Right? We've just, all I've done here is I've split this up into 2 components. To get the mean square, well, hold on, that's just the variance. Divided by n minus 1, big N minus 1, that should be big N. Big N is the total. There are k groups, so it's k minus 1, because what k means divided minus the grand mean. And this one is big N minus k. What? How's that big N minus k? Well, when I do 85 minus 84 squared, 90 minus 84 squared, and 77 minus 84 squared, right? How many degrees of freedom did I have when I did this? When I did that sum of squares? This minus this squared, this minus this squared, and this minus this squared. How many degrees of freedom? 2. Yeah, n minus 1. All right. How many times do I have to do this? This minus this, this, this. Oh, I got to do it 3 times. Well, this hard. K times. K times n minus 1. K times n minus k. Just expand it. K times n, number of groups times number of subjects. That's big N minus k. Hey, algebra. There's a reason it's big N minus k. It really is k times n minus 1, but a nice shorthand is just saying big N minus k. It's just algebra. Again, questions? So when you are calculating these things, this is in fact how you calculate them, or how a computer calculates them for you.
Will we be doing that?
Yeah.
Can you show us?
We can do one in a second with those those
Okay.
actual numbers right there. Okay. Oh yeah, good. No, anybody else? Any other questions? We're good? Okay. What you get at the end of this is what's called an analysis of variance summary table. You have sources of variation between groups, within groups, or treatment and error, and then total. Degrees of freedom, k minus 1, big N minus k, n minus 1. By the way, if you add up k minus 1 to n minus k, you get big N minus 1. Because look, k minus 1 plus big N minus k, oh, k minus k, the k's come out, n minus 1. It's not what they're supposed to. The mean squares, sum of squares between groups, which I wrote that way this time, mix it up a little, or sum of squares treatment, divided by k minus 1. Sum of squares within groups, or sum of squares error, divided by big N minus k. And then f is mean squared between groups divided by mean squared within groups, or mean squared treatment divided by mean squared error. They're the same thing. We then take the f that we have, we look it up in an F table and see with the requisite degrees of freedom, with k minus 1 and n minus k degrees of freedom, and we see if we exceeded the critical value. That's all it is. It is not magic. If it was a card game and all, it'd be Cards Against Humanity. It wouldn't be magic. Thank you. There's nothing more fun than playing Cards Against Humanity with your mom. It's great.
No.
With your mom and your sister and your brother and like my sister's boys who are like teenage boys. It's so fun embarrassing my mom in front, or even better, watching my mom embarrass her grandchildren. It's wonderful. Okay, questions about this? Because we can work through one of these in a second. You good? All right, so we'll stop this.